convergences in the presence of D-instantons when we try to carry out string perturbation theory in that background. Okay. And then we also described how to solve this in using string field theory. Okay. So, what we will do today is to work out some specific example, okay, and we will see that we will actually need more than what we have discussed so far. Okay. So, I will begin by giving a brief introduction to the worldsheet theory. So, here we will have the matter theory, which has a C equal to 26 CFT, and the ghosts, okay, which we have B, C, B bar, C bar. I should say that I am considering bosonic string theory here, but the same discussion can be carried out for superstrings. Okay. So, these have conformal weights. This is 2 0, minus 1 0, 0 2, and 0 minus 1. Is there a way to? Hello? This is hello. Hello. Okay. So, for the matter CFT we will not assume very much, okay, except that we will assume that we have a time direction, Euclidean time direction, which I will denote by x, okay, and then some C equal to 25 CFT, okay, which could be say 25 free scalars, which corresponds to the 26 dimensional bosonic string, or it could be a C equal to 25 Liouville, okay, which will be 2-dimensional strings and so on. Okay. Basically, we will be working mostly with this one. Okay. So, since every CFT has a state operator correspondence, okay, and since string states are states in CFT, so for every string state you have a vortex operator. Okay. In particular, closed strings have a vortex operator in the bulk of the worldsheet, whereas open strings, okay, for example those that live on the D-instanton, have vortex operators on the boundary, have vortex operator on the boundary. Okay. And here bulk and boundary of course refers to the worldsheet. Okay. Let me also say something about the boundary conditions. So, the boundary conditions, in the ghost sector we put B equal to B bar, C equal to C bar, okay, and on the matter we just use Dirichlet, okay, Dirichlet along x, because that is certainly a non-compact direction, and other non-compact directions which we will not care about for now. Now, as we discussed last time, okay, there is one particular class of states which will play an important role, class of open string states, and those are the zero modes. Okay. So, in particular there is an open string 0 mode that corresponds to time translation, that is translation along time, because the D-instanton is localized along some particular value of time, okay, that is encoded in the boundary condition. You put x equal to some constant, okay, that constant the boundary condition, but you can of course move that, change that constant, and that is captured in some open string 0 mode. Okay. So, you can ask what is the corresponding vortex operator for the 0 mode. Okay. And here the answer, there are two kinds of vortex operators that we will be working with, okay, and I will describe the significance later. Okay. So, we can either describe this by what is called the unintegrated vortex operator, which is just del x, okay, where x is the time direction, sorry, which is c del x, where x is the time direction, the scalar field corresponds to the time direction, okay. C is the c host, okay. And here it does not matter whether you are using c or c bar, because this is an open string vortex operator inside of the boundary. So, c and c bar are the same. Similarly, del x and del bar x are the same.
So, del is the normal derivative.
Yeah, it is a normal derivative. Okay. And then you have integrated vortex operator, which is del x. Okay. So, from the string field theory perspective, this is more fundamental, okay, because you normally always start with unintegrated vortex operator and then sometimes arrive at integrated vortex operator. Okay. But for practical purpose, okay, which is what we are going to do today, okay, let me just say what role they will play, okay, or what role they play in normal worldsheet perturbation theory. Okay. And the way we make use of these, okay, is the following, okay, that if you take a Riemann surface, okay, then there may be conformal killing vectors. There may be CKV, okay. So, these stand for conformal killing vector. So, these are like killing vectors, but up to conformal transformation, okay. And using these, okay, we may sometime fix the positions of some vortex operators, of some punctures. So, punctures, let me remind you, are just fixed marked points on the Riemann surface where the vortex operators are inserted when you actually do worldsheet calculation. Okay. So, the idea is that at the fixed punctures we use the unintegrated vortex operator. Okay. So, use the unintegrated vortex operator, unintegrated vortex operator at fixed punctures, and integrated vortex operator at moving punctures. Okay, moving punctures means we just integrate over the positions of these punctures when calculating amplitudes. So, let me discuss a simple example. Okay. So, we denote the 0 mode by phi, okay, and you want to compute say phi amplitude on disk. Okay. So, this corresponds to taking a disk and inserting 4 of these vortex operators for phi. Phi is the 0 mode, And the idea is that when the positions are fixed, we will use C del x. When the position is variable, we will use del x. Okay. We will make it more explicit in a few minutes.
You will eventually be interested in the 2-point function. Is that right? The reflection coefficient?
Yeah, for closed strings, right? But I mean, this is general, right? I mean, we will be interested in many things, right? If you want to calculate the instanton, basically we will want to calculate closed string amplitudes in the presence of instantons. But as we discussed, when you have instantons present, we have to allow also the open strings in the background for the intermediate calculations.
But for the calculation for the Z, to compare with the Z stuff, you want a 2-point function of the closed string.
That's right, yeah. Okay. With arbitrary insertions of open strings.
Expectation is that this is u raised to e to the IPX.
Yes, that's right. Okay, we'll discuss what it is expected. Okay, and then we'll try to see how to get there. Okay. So we'll be using actually the upper half plane coordinate. So disk is equivalent to upper half plane. Okay. And the relationship between the coordinates is simple. So you can write the coordinate on the disk is 1 plus I z UHP over 1 minus I z UHP. Okay, and we will use upper half plane. Just to make life simple, we will use UHP. Okay. So upper half plane is basically upper half complex plane. So we will denote this z by z, the coordinate on the upper half plane. Okay, and that's the only description we will be using from now on. Okay, for the disk. So basically these 4 vertex operators get mapped to 4 points on the upper half plane. Okay. And on the upper half plane there is an isometry, there is a conformal isometry. Okay. So conformal symmetry which is SL2R.
Sorry, I'm completely embarrassed, but I don't
Yeah.
know where that formula comes from.
This one?
Yes.
Okay, this is, you can easily check that when this takes value on the upper half plane, right, this takes value on the disk, right. In particular, look at the boundary, right. Z upper half plane is real, right. So for that, if you take the absolute value of this, that is 1, because it's 1 plus I times real, 1 minus I times real, right. So absolute value is 1. So the boundary of this, right, maps to the boundary of the disk. Okay. Then
This is like the confirm. I thought you were saying partition function.
no, just coordinates. Yeah.
Then
Yeah. So we are not at a partition function yet. There is just the coordinates. Yeah. Okay. So the idea is that there is an SL2R isometry. Okay. And using the SL2R isometry, sorry, let me write the SL2R transformation because it will be useful later also. Okay. So Z goes to AZ plus B over CZ plus D, okay, with A, B, C, D real and AD minus BC equal to 1. Okay. So using this SL2R isometry, we can keep 3 of the points at 0, 1 and infinity, okay, and the 4th point as at some variable value y, okay, because it has 3 parameters, right. Out of the 4 there is one condition. This side board, okay. This doesn't move, I think, right? Or it moves? Oh, I see, okay. Okay, that's good. Then let it be there.
Ashok, there are 3 disconnected choices for where we can put y, right?
Yes, that's true. So I'll discuss. So the point is, because all external states are the same, right, you can just put y anywhere. It doesn't matter. If the external states are different, then you have to sum over all possible choices of y, right, whether from 0 to 1 or 1 to infinity or between minus infinity. And so all of these have to be done, but because the external states are all the same, right, you just put y between 0 and 1. Is that clear? Okay. So then what we have to calculate the amplitude, okay, up to a constant of proportionality, because you have this factor of 3, right? Y could be written 0 and 1 or 1 and infinity and so on. Up to that, okay, its integral dy from 0 to 1, and then the expectation value of c del x of 0, c del x of 1, c del x of infinity, and then del x of y. Okay. So, this can be easily evaluated. Okay. So, we have this relation C of Z1, C of Z2, C of, so on the disk, because of the conformal anomaly in the ghost sector, we need total ghost number 3. Okay. So, I should have said C by definition carries ghost number 1, B carries ghost number -1. Okay. So, this is non-zero on the disk, and this has the structure Z3 minus Z1, Z3 minus Z2, and Z2 minus Z1. Okay. And this correlation function this is basically Z1 minus Z2 to the -2, Z3 minus Z4 to the -2 plus permutations. Okay, basically 2 more terms. Right? You can just have Z1 minus Z3 to the -2, Z2 minus Z4 to the -2, and so on. Okay. So, using this, we can evaluate this, and it is a simple exercise to check that this becomes 0 to 1 dy y to the -2 plus 1 minus y to the -2 plus 1. Okay, so, this is the kind of integral that I wrote down last time. Okay. And as you can see, this integral is divergent from y equal to 0 and y equal to 1 because of these factors over here. Okay. And our goal will be to try to use string theory, field theory to make sense of this integral. Okay. But before I do that, let me just say a few words about why you want to study this amplitude, right? Because earlier we had said that the kinds of amplitude that you are interested in has closed strings and open strings, right? Closed strings are the main things, right? And but you are forced to put some external phi's. Okay. This is an amplitude with only external phi's, right? So, why should we worry about this? And the point is that this amplitude can still come as a subdiagram of amplitudes like this, right? Since for D-instantons we are also including disconnected diagrams, right, in the calculation of 2-point function of closed strings, right? This is one possible diagram. Okay, closed string here, and then 4 open strings. Right? So, we have to evaluate this if you want to calculate closed string amplitude. Okay. So, we will just focus on this just because it is a simple example, okay, which you have to evaluate and which has a divergence of the kind that we will encounter in general. Okay. And the point is that once you understand how to repair this, right, exactly the same procedure will hold for arbitrary diagrams. Okay. So, it is a simple example that we can use to test our procedure. Is this okay? Okay. So, the idea is that the regions near y equal to 0, y equal to 0 and y equal to 1, okay, where the divergences are coming from, okay, they are somehow associated with Feynman diagrams, okay, maybe something like this and this. Okay. And remember there is a skew parameter associated with propagator, okay, and the kind of we said that the divergences in string theory, okay, from the perspective of string field theory always comes in the q goes to 0 limit, okay, because what we were trying to do is that you are trying to represent 1 over m square as integral 0 to 1 dq q to the power m square minus 1. Okay. This is true for positive m square, For negative m square, this is fine, the right hand side is not is divergent, right? And for m square equal to 0, both sides are divergent, right? But that we know what to do. Okay. So based on this, we arrived at this idea that at this stage the way we should regulate is that whenever you encounter something like integral 0 to 1 q to the power beta minus 1, okay, we replace it by 1 over beta, okay, for both beta positive and beta negative. Okay. For beta positive it is an identity, for beta negative this side is divergent, this side is finite, okay, and we replace it by 0 for beta equal to 0, okay, because beta equal to 0 is a genuine 0 mode, right, and setting it equal to 0 basically means that you just remove that 0 mode propagating in the intermediate state. Okay. So that is the procedure you want to follow. Okay. So then the idea is that to make sense of that integral, okay, we will try to go close to y equal to 0 or y equal to 1 and try to find a map between y and q. Okay, you have to understand how to go from y to q. We express the integrand in terms of q and then use this procedure, okay, to remove the divergences.
Suppose for a moment it was a different problem. There was some other non-compact direction in which you had Neumann boundary conditions.
Yes.
So we could have then had momenta in those Neumann directions.
Yes.
And we could then have defined that amplitude in the usual way.
And analytic
And
continuation.
analytically continue to p equals 0.
Yes.
Will your final answer be the same as that procedure?
If you did, so that means if you didn't, instead of D-instanton, if you had some
Yeah.
other,
Yes. I mean,
Yeah.
for these vertex operators, it's not very important, right? Because you're just
oh, whether that, yeah. So the point is that then what we have to do, right? You see the when there are external momenta, right? There are also additional almost massless states which are flowing in, right? So those depend on models. I mean, what extra directions you have, right? And you have to subtract those.
and that will be complicated.
Yeah, that will be complicated. So it's not.
It's not a clear question.
Yeah, it's not a very clear question, right? Because there will be additional massless states now, right? Which are almost going on shell, right? When you are trying to go into 0 momentum limit.
Diagrams you drew on top to say why this amplitude with no close string nodes but just the disk and 4 insertions of phi arises.
Yes.
I wasn't sure. I mean, there are different orders in G string.
No, it is the same diagram, one diagram. You have one term, product of all these, right?
Some order in one of one.
Yeah, so some order in one of the string, you will get product of this, right? So you have to understand this, right? So that's the
It's got 2 insertions of close strings, but it's
exactly, right? So this part of the calculation will just involve that integral.
Like a sphere with a hole cut out in which and 2 insertions of closed string vertex operators, but those are very far away from the.
No, it's not a it's not a connected surface. It's really disconnected.
No, but in the limit of limit of when these closed string insertions are very far away, then they get pinched off. Or is that the point? Or
No, see here the this is finite, this is finite.
yeah.
Okay. This is divergent, right? So here the pinching is because I mean the y goes to 0 limit will correspond to when 2 vertex operators come together, right? So if you think in terms of pinching, right, that diagram, this is a single disk. When you have 2 open string vertex operator here and 2 open string vertex operator here, that's the pinching. So pinching is happening in this diagram. These are totally disconnected.
So how does this appear?
Because you don't have energy conservation on individual diagrams, right? See normally, I mean see you always have disconnected diagrams even in quantum field theory, right? The reason that you don't consider them is because they are separate energy conservation, then it will get separate energy conservation, right? So there will be product of 2 delta functions instead of having single delta function. So that's a codimension 1. You can just ignore those forward scattering amplitudes. Here the energy conservation will come at the end after you do the integration over phi, right? So the fact that the individual diagrams have no energy conservation anyway, right? So that's why these diagrams are as important as a fully connected diagram. Right? There is no way you can distinguish these from the fully connected ones. Yes. Yeah, see, it's not the volume, it's also that there is an integrand, right? So it's not really the volume of the moduli space, because I have 4 vertex operator that has been inserted. Exactly. That's right. Exactly. That's right. So as you go towards the boundary of the moduli space, there are divergences of the integrand, right? And that's what you want to see how to regulate.
Sorry, Ashok, I'll ask my question again. Probably stupid there. So what we want to do is to find a 4-point function of this del x, del x, del x, del x.
Yes.
Now suppose we enlarge this to finding 4-point function of del x times e to the power ip x prime, where x prime is some other conforming field. In the limit that p goes to 0, that ip x prime is going to identity.
Yes.
So in the limit that p goes to 0, you've not changed the answer, you've just multiplied by this partition
Yeah,
function.
but see what happens is that if, as you take p goes to 0, right, that when you take finite p, ip x prime, there is a del x prime that is flowing,
Okay.
right? That doesn't go away in the p goes to 0
Yes,
limit.
p goes to 0 limit is somewhat
Yeah, exactly, because the point is there is a vertex contribution which is which has powers of p in the numerator, and the propagator has a 1 over p square, right?
Wait, this would be actually an open string scattering amplitude. So the p goes to 0 limit should not be singular.
So it's not singular.
But it's just the wrong limit.
Exactly.
You're saying the limiting procedure doesn't give you the
Exactly,
value
because it's like Young-Mills, right? If you try to calculate the 4-point function and take the k goes to 0 limit, right?
Yes.
There is a 1 over k square pole,
Yes.
right? That cancels the 2 factors of k from the vertex of the Young-Mills vertex,
Thank you.
right? So it doesn't really go away.
Thank you. So just if you did that, you would get a different answer. From
Yes, you'll get a different answer. Yes. No, there will be okay. There will be qualitative difference if there is different particles, right? But here, because you have all external states the same, right? Once you get the y equal to 1, the same answer will be valid also for y equal to 0. Okay. So the question is, find y to q relation near y equal to 0 or y equal to 1. Okay? Yes. Well, del x is on shell, or C del x is 0.
So that will automatically, isn't it true that that's automatically constant the delta function in the momentum conservation or the energy conservation on the voltage?
No, because here you have okay, in this case it will not, because everything carries 0 momentum anyway. See, in this case everything carries 0 energy anyway, right? Because open strings don't carry energy. But suppose you had a 2-point function of closed strings. Okay, this will still have a degeneration like this, where, so here you have closed string, here you have closed string. What flows in through here, right, has 0 energy, even though those carry energy, right? So you don't have energy conservation in the intermediate channel because the boundaries can absorb energy, right? The boundaries are energy non-conserving boundary condition, because you are putting Dirichlet boundary condition on the boundary of the world sheet. Okay, now before I go on, let me just say what to expect for this. What answer do you expect? Okay. So that can be guessed by noting that this phi is related by field redefinition to the collective coordinates I. Yeah, yeah.
Since there's no photon 3-point function, I mean in Young-Mills there would have been.
Yes.
Between this one.
Yes.
So the thing that flows in the middle can't be one of the photons.
No, because the external particles are e to the ip dot x prime. External particles are not photons.
They tackle it.
Yeah, because you are putting e to the ip dot x prime, right? Yeah. So they actually carry the charge. There are momentum. The del x couples to the momentum basically.
But are the tachyons charged under the gauge symmetry?
Well, see this is okay. That of course comes from a Chant pattern factor, right? But if you are just calculating the amplitude, the kinematic level, right? Then there is a non-zero 3-point function.
It cancels between the channels.
Exactly, that's right.
So in any one channel it's there.
Exactly.
Thank you.
Yeah. Because otherwise the young mills will not get, right?
Yes, yes, yes. The
Yeah.
angles, it removes the cancellation.
Exactly, that's right. Because that the different Chant pattern factors. Yeah. Okay. So we saw that the phi is related to the collective coordinate xi, right? And xi dependence we know is trivial. It should be to the I p dot xi, where p is the total momentum that is flowing into the diagram. Okay. Now here p is 0, right? Because our diagram is only open strings in the external state. So this part has no energy flowing in. Okay. So we expect that this should be 1. Okay. So the xi dependence should not be there, right? If you think in terms of collective modes, right, the amplitude should be independent of the collective mode. Okay. Now, if we had a non-trivial function of xi, then under a field redefinition that could become another non-trivial function. But 1 cannot become anything other than 1, right? 1 is just constant. Okay. So even when you use phi variable, the 1 is 1. Okay. So which means that amplitudes shouldn't have any phi dependence. Any amplitudes of this kind, right? However many phi's you insert, okay, it should just be 0. Okay. So xi to phi, okay, still gives 1. Okay. So no phi dependence.
As you said, this is because there are no closed string insertion.
Exactly, because there are no closed string insertions in this diagram. Okay. So what we expect is that this should be 0. So the amplitude should actually be 0. Okay. But we want to see how the 0 comes by doing this integral. Right. The reason being that here we know the answer, right? So we should test whatever we the general procedure that we have described, okay, for this, because if it doesn't work for here, right, that means that it will not work in general. Right. Okay, phi you are talking about phi dependence, right? See 4 phi is inserted. So if this is non-zero, that means the phi to the 4th term is non-zero, right? But there is no phi to the 4th, there is no phi dependence, right? So any number of phi's inserted on the disk should give you 0. Is this clear? So how to get 0 is the question. Now, so for this, okay, since we are trying to relate it to a diagram like this, okay, we know that ultimately the y and q relation that we are trying to find is q will come from a diagram of this kind, right? It does not matter which one, because since all the external states are the same, S, T, U channel are all the same, right? So just focus on this. Okay. But this understanding this diagram of course requires this 3-point vortex, right? Because after all, what is Feynman diagram? You take 3-point vortex here, 3-point vortex here, multiply the propagator. Okay. So you need knowledge about the 3-point vortex from for the string field theory diagrams. So the naive expectation, okay, will be that if we have 3 vortex, 3 external states described by vortex operators V1, V2 and V3, the 3-point function will be something like this. Okay. The problem of course is that this 3-point function depends on the z's. Okay. And the reason that it depends on the z's is because the v's are not on shell in general, right? If you look at a diagram like this, okay, you see these are on shell, these are C del x, okay, so these have no problem, they are dimension 0 primaries, but this one can be anything, right? That's what in a field theory the internal states are never on shell. Okay. So we need at least one of the vortex operators to be off shell, okay, and if that's the case, okay, then this depends on Z1, Z2, Z3. So this depends on Z1, Z2, Z3. Okay.
If you're interested in just pole contribution, then it's just the on-shell 3-point function.
Yeah, but we are interested in little more than a pole contribution. We will see that, I mean, because we have to extract a finite piece also, right? If you want to just so the pole contribution cancels, that you may be able to do, but the goal is to extract a finite piece.
And then if you're interested in more than the pole contribution, there's no possibility of contact terms in addition to these exchanges?
Yes. So, there is this. This diagram is always there. Right. So, the point is, as we discussed last time, that what will happen is that this diagram covers part of the y integral, right. The other diagrams cover other part, and this one fills the rest. Right. So, basically, yeah. So, the point is basically what will happen is that the regions near y equal to 0 and y equal to 1 will come from diagrams with propagators, okay. And then the leftover region will be covered by the contactor. Right. That is the way string field theory produces the amplitude.
I think I'll make one last comment about next to the thing.
Yes.
Suppose you did some over channels, I think you would get 0 in that case. Because you would just get you can get f to the 4 terms basically. And then you take momentum to 0, you
Yeah.
get 0.
Yeah.
So in this particular case it would work.
Yeah. Meaning the one in this particular case, of course, you know it works in many ways, right? Because this is like a marginal deformation in a CFT. Yeah. Okay. So already we see that there is an ambiguity. Okay. What string field theory does is to make it more ambiguous. Okay. At least at the intermediate stage. Okay. So it says, okay, since it's ambiguous anyway, okay, so let's make it more ambiguous. So the general form of the vortex that string field theory gives is, let me write it this way, S f1 dot v1 0, f2 dot v2 0, f3 dot v3 0. Okay, I'll explain what this is. Okay. So S is easy to understand. Okay. This is symmetrization. Under permutation of v1, v2, v3. Okay, any vortex must be fully symmetric, right, under the exchange of external states. So the notation f dot v of w, okay, this means conformal trans, okay, so f I should say, so f1, f2, f3. So f1, f2, f3, these are 3 conformal maps, at present arbitrary. Okay. They need not even be SL2R, okay, any 3 conformal maps. F dot v of 0 is by definition conformal transform of V under F. Any conformal map at present, right? Later on we will fix it, but at present it is some conformal, any conformal map which is well defined inside around a certain region near the origin. Right? That is all you need. That because otherwise you are making the conformal map around 0.
These are primaries, etc. of some way.
Not necessarily, V can be secondary. V is arbitrary open string state, right? Off shell open string state flowing, so that can be arbitrary. Okay. So, example, okay, that if V is dimension H primary, then F dot V of W is F prime of W to the power H V of FH, sorry, V of FW. Right? This is the way dimension H primary transforms. So, for example, I should have said that I have not separated between left and right conformal dimension because this is all happening at the boundary. right. So, it is a total conformal dimension, left plus right when you do the counting. So, f dot c is f prime of w inverse c of f w, right, because c is the dimension minus 1 primary. So, let us do one more example, f dot del c of w. So, this is del w of f dot c of w. So, which is del w of f prime w inverse c of f w and this you can work out, this is del c of f w minus f double prime w over f prime w square c of f w. Okay, so this shows, and this basically this part shows that it is not a primary, right, the additional transformation laws. Okay, this part basically reflects that it is a dimension 0 because there is no f prime w. F prime, no, this, no, because when you say del w on c, right, because there is a f prime w which comes out. Del c means the differences with respect to its argument.
So the first term is the usual tensor you think.
Exactly.
If LC was a primary, that's what.
Exactly. If the LC was a primary of dimension 0, then this term would be the only one, right. This is the extra term that is telling us that it is not primary of dimension 0. Okay. But the point is that given any any field, you can calculate its transformation law, right, and that is what you have to put in here in this.
And the square bracket means expectation value.
Yes, this means expectation value on the sphere, on the disk.
On the disk, and that is the 3-point
Function of 3 open string states, V1, V2, V3.
coupling between these 3 modes in string field.
Exactly, that is right. This is a coupling between these 3 modes in string field theory.
So Arvind mentioned this 0 is what? This V1 of 0, where is it?
Well, that's with W is 0. You just put it at 0.
But everything is happening on the boundary, right?
Yes, that upper plane.
And this 0 is where?
So W equal to 0, right?
The x equal to 0.
Yeah. You see, just look at the definition, right? The f of 0 will appear in the argument of v, right? So this means that v1 will be placed at f1 of 0 with some factors, right? v2 will be placed at f2 of 0 with some factors. So if the fi of 0 are the locations of the vertex operators on the boundary, right? And then there are some factors that comes from all this analysis in general. H, there are infinite number of h's, right? So it starts from 0 and then it goes up. In fact, it starts from -1 and then it goes up. No, not below -1. -1 is the lowest. Two? Yes. Exactly, that's right.
That bracket is supposed to be that bracket or
Which bracket?
the first expectation value?
Yes. So this one is just a 3-point function on the sphere. Right? So the point is you first calculate all this, right, and then you calculate the 3-point function on the sphere of whatever comes, whatever operator comes. On the disk, yes, sorry, on the disk, yeah.
Is it okay to think of f i's as terms of conformal maps or something from the Dirac or locally defined?
Yeah, these are all locally defined. I mean, they don't extend all the way to infinity, yeah, but locally, yes, locally you can think of this as some conformal, I mean, you can express this as exponentials of ln's, right, yeah. No, all the v has an outer center point equal to 1, 0, w is 0, right. So the first v is set at f1 of 0, second one is at f2 of 0, third one is f3 of 0, right. The fact that w is 0, that's a matter of convention, right. That's you have to put it somewhere. So w equal to 0 is by convention is where you put. Yes, F's are real. Yeah, F's are real maps in this case, right? For closed strings, they don't have to be real. In this case, it maps onto a real line, exactly. Yeah, otherwise, of course, it doesn't make sense. Yeah.
Can you ever see different conformal maps in the same 3-point function?
Why? Because it's the most general thing, right? Because see, if you want the same conformal map, then all of them will map at the same point, right? But that's singular, right? We want to define a 3-point vertex which is non-singular, right? So you want them to be different, but the precise choice is up to you, right? That specifies the string field theory, right? Now the point is that you can say, okay, there are an infinite number of string field theories because you can choose F1, F2, F3 anyway, right? And the point is indeed there are infinite number of string field theories. What we can show, however, that all these string field theories, these infinite number class of string field theories, are related to each other by field definition. So the physical amplitudes, any physical quantity that you compute, should be the same. Okay, they shouldn't depend on how you have chosen these F's.
Sorry, just to understand that, you can choose many conformal maps such that, say, F, where it vanishes corresponds to some zero. And in that way, you don't have a one-to-one map clearly between the conformal maps and the original locations.
Yes.
But despite that, and that corresponds to some field redefinition.
Oh, it's not as easy. Yeah, no. The field definition is highly complicated. I mean, it requires a lot of effort to show.
But
Yeah.
at least it corresponds to that, right? The different choice of the maps corresponds to the field. Or is a subset
See, the
of-
point is it's not linear field definition, right? It requires a whole set of vertices to actually show that they are related by field definition, right? So, for example, once you have chosen the 3-point vertex this way, the 4-point vertex has some constraints, right? The 4 phi interaction, this contact interaction that Siraj just mentioned, right? That is not completely arbitrary, right? It has to be chosen in a certain way. After you have satisfied all those consistency conditions, only then you can show that the choices are related by field definition. But it's not trivial. We will see that there is a non-trivial dependence on these maps at the intermediate stage. Okay. In fact, what we will see at the end of today's lecture, it would indicate that it doesn't seem to be independent of field. It doesn't seem to be independent of the choice of these Fs. Okay. So it's not. I mean, you have to do some work to make sure that everything is fine. Okay. So let me now give the choice that I'll be working with, and I'll then discuss why that particular choice. Yes.
Here, one wants to extract a number which is to be the 3-point function.
Yes. Well, if you are interested in a 3-point function, that's what we would want to do. But we want to use this 3-point function to actually calculate the 4-point function.
But just for the 3-point function, where are we going to get the number from? Because everything is still a function of z and so on.
Oh, but then you have to calculate the correlation function, right? On the 3-point function. So z's are all fixed by f's. So once you have chosen the f's, right? All these are completely fixed, right? Because they are evaluated at w equal to 0, right? You put that back, calculate the 3-point function.
Choice of f is a choice of string field.
Yes, choice of f is a choice of string field theory. So the actual 3-point function will be different in different string field theory, right? For off-shell states. For on-shell states, it will be the same because dimension 0 primary, right? All of these will be trivial, right? But for anything else, the 3-point function will be different.
And as you said, Ashok, even if you chose f equals z,
Yes.
there would still be an ambiguity because it would be like where you put the.
Yes, exactly. I mean, if you put say f1 equal to z, right? f2, you know, it's not z anymore because then things will be on top. You have to put some z minus 1, say,
Yeah.
right? And
That's the choice of putting it at.
exactly, that's it.
So even for constant,
Yeah, yeah,
that the basic ambiguity of the fact that your 3-point function depended on where you put.
exactly, that's right. Okay, so our choice will be as follows: f1 of w, let me call this w1, or maybe I should have said something else, but I'll say that afterwards. Okay. So, before I explain the advantage of choosing things like this, let me just say one thing, okay, that once you have chosen this f1, f2, f3, we can define what are called local coordinates. Okay. So, suppose z is the coordinate on upper half plane. Okay. This we will fix for once and for all. This is the coordinate on UHB. Okay. So, we will define W1, W2, W3, define W1, W2, W3 via Z equal to Fi of Wi. Okay. So, Z is F1 of W1, Z, the same Z is F2 of W2 and Z is F3 of W3 around. So, this makes sense only around Wi equal to 0, okay, because we are not assuming necessarily that Fi of W is globally defined function. Okay. It may have branch cuts, various things. Only thing you are assuming that near W equal to 0, it is a smooth function. Okay. So, that otherwise this will not make sense. Okay. That near W equal to 0, it should be differentiable, for example. Okay.
So can I think of it in this way, that you have the space of string field?
Yes.
You have some coordinate where you can have some diffeomorphism invariance, and this is fixing a gauge.
Well, so far from the field theory viewpoint, we are not fixing any gauge. We have not even seen any gauge invariance, right. So, from the field theory perspective, we are just fixing a prescription for defining the field theory. Then it will have its gauge invariance and I will fix it, right. From the worldsheet perspective, you can say, okay, it is like fixing a gauge, but it is not clear that the 3-point function is gauge invariant. It is not in general, right, because for off-shell states, but it is just choice, some choice you are making. Okay. So, these Wi's are known as local coordinates.
Can you give some explanation as to why this definition of string field is so ambiguous? Why is there, what does this mean?
Because you are trying to deal with off-shell states, right, and the off-shell 3-point function from the worldsheet perspective is ambiguous, because it depends on the choice of the worldsheet metric, right, and this what the f's are capturing is in some sense choice of worldsheet metric that you are using to define the amplitude. But the point is that it actually does not depend on the choice of worldsheet metric everywhere, right. If you have a 3-point function, you expect that the result will depend on the choice of worldsheet metric near the punctures where the vertex operator is being inserted, right, because that is what is violating conformal invariance. And these f's are basically a way to parameterize what choice of worldsheet metric you are using. Okay. Maybe that you can also say in this language. So, these Wi's are called local coordinates. Okay. So, what we can show is that definition is equivalent to saying that when you insert the vertex operator, right, you are inserting it in a coordinate system in which the metric is mod dwi square. Right. That around the first puncture you are using the metric mod dw1 square, around the second puncture you are using the metric mod dw2 square and mod dw3 square, but then you have to calculate it in the upper half plane, right. So, you have to convert from the w coordinate to the z coordinate, right, and this is basically converting the vertex operators from w coordinate to z coordinate, and then you calculate the 3-point function, right. So, the ambiguity is basically ambiguity in what metric you choose near the vertex operator. Yes.
To be clear with the logic, at this stage you could have just gone ahead and computed that 3-point function here written on the top without going into all this.
Yes, yes. That is a special case of this.
Right. But at the end of it, you're saying that it doesn't give enough to interpret this 3-point amplitude.
No, it gives enough. It just does not have enough freedom, right. You want to see that ultimately everything should be independent of the choice of the f's, right. So, that will correspond to some particular choice of f, right. Like as Siraj was saying, that will correspond to f1 of z as z minus z1, f2 of z as z minus z2, and f3 of z as z minus z3, right? Or the other way, sorry, f1 is w minus z1, yeah, f2 is w minus z2 and w minus z3, right? That's, but yeah, so that's just a particular choice, right. This is a more general class of choices.
So we are encoding all the ambiguities that are present in an off-shell 3-point perturbation over G.
In terms of this, exactly.
That's the, in some sense, biggest ambiguity that
Exactly, that's right. No, yeah, we are always at the boundary of the upper half plane, because the vortex operators here inside the boundary. When you have closed strings, then of course the punctures are inside. Right? There you are choosing local coordinates around those punctures. So WIs are always local coordinates around the punctures. Yeah, but see, that will automatically be done by the correlation function, right? Because the correlation function is that the theory is conformal invariant. Yes.
You want to have the worksheet is being mapped, going to be mapped inside the bulk.
Yes, but that mapping, so the bulk, the fields are all integrated over. Okay. After doing that, you know the theory is conformal invariant, right? So what metric you choose on the worksheet is irrelevant, right? So the only thing that matters is what metric you have chosen near the boundaries, because that's where conformal invariance is getting broken. Okay, so now let's see what is so special about these. Okay. First, you see that each of these is SL2R transformation. Okay. It's not necessary, but it will make our life infinitely simpler. Okay, because there are SL2R transformations. So that's the first point. First point is SL2R. Okay. Second is f1 of 0 is 0. f2 of 0 is 1 and f3 of 0 is infinity. That you can see, right, from this. So that's just saying that the three vortex operators will be placed at 0, 1 and infinity by this procedure. So 0, 1 and infinity are just conventions. The key advantage of using this is in the third step. So you see, consider the SL2R transformation, z goes to 1 over 1 minus z. Okay. So this maps 0 to 1 to infinity to 0. Okay. If you work out a little carefully, you will find that this also maps f1 to f2 to f3 to f1. Okay. So this means that if we make the choice this way, it's not necessary, but suppose you do it this way, okay, then the 3-point function, okay, that f1 dot v1, f2 dot v2, f3 dot v3 is already cyclically symmetric, because you can make SL2R to make f1 to f2, f2 to f3 and f3 to f1, right. So the vortex is already cyclically symmetric. So that symmetrization, right, only has to make it fully symmetric. Okay. But furthermore, okay, if you look at the amplitude that you are interested in, there is phi 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 phi. In the intermediate stage, some state is propagating. So the vortex for which you have to evaluate this already has two external states identical. So if you have two identical external states, then cyclic symmetry means it's fully symmetric, right? So that symmetrization you don't have to worry about. So you just have less number of terms, right? You just work with that one vortex and that's it. So symmetrization automatic. And you can in fact check that this is the most general vortex that satisfies all these properties, right? Because first of all, let's take f1, right? SL2R already tells that it has at most 3 parameters. If we demand f1 to be SL2R, right? Then you are saying that f1 of 0 should be 0. That already fixes 1 parameter. So it has only 2 parameters. That's alpha and gamma. Okay. Once you have fixed f1, then f2 and f3 are fixed by demanding this. Then you just make z2 1 over 1 minus z, whatever you get will be f3, f2, and then from there again you will get f3. Right? So this is the most general vortex which satisfies all these nice properties. So you will work with this vortex.
And it's probably not important, but is this equivalent to choosing a particular choice of metric on the?
Yes, That's right, because it corresponds to, as I said, metric is, once you see the W, right, the metric is mod dW1 square, mod dW square and mod dW3 square around the punctures, right. So, it does correspond to choosing particular metric.
But you could choose a global metric or the whole.
Arbitrarily, because global metric, the theory is still conformal invariant, right. So, how you choose a metric away from the punctures is not relevant, right. Only thing that matters is what the metric is around the punctures, right, because you are breaking conformal invariance by the vertex operators.
In the Z coordinate, do they go very far off to these corners become very long?
In the Z coordinate, not really. In this form, the corners don't become very long, right, because it's perfectly, there's no infinity, alpha and gamma are finite numbers, right. But we'll also work with large alpha, okay. Again, this is not necessary, just to make life simple. Right now, we don't need to worry about it, but let me just state it anyway that we will.
The ambiguity defining the metric is up to a comma, right?
Yes.
But here, if we consider endpoint functions are n independent.
Well, but the point is these are all near the neighborhood, right. A function is defined everywhere, right. This is where these f's are only defined near the neighborhoods of the punctures. Okay. So, now I am going to state a result without proving, right. Next time we will try to, indicate how that comes, right, but I will just state a result and then proceed with that. Okay. So, let me remind you what the problem was again. Okay. So, we have phi, 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 phi. Okay. This propagator has a q parameter, right, because 1 over m square I am writing as integral 0 to 1 dq q to the m square minus 1. Okay. We want to know how this q parameter is related to y. Okay. So, q y relation is what we are trying to figure out. Okay. I will give the algorithm that does this. Yes. Now, we are going to glue the two 3-point functions into a 4-point function, right. So, basically pictorially what is happening? We have this 3-punctured disk, we have another 3-punctured disk, right, and we want to somehow connect them by a propagator, right. Okay. So, geometrically, okay, what is going to happen is that we are going to claim that this becomes a disk like this. Okay, the effect of connecting, basically you are summing over all states connected by a propagator with a propagator inserted. Geometrically, it becomes something like this, a 4-punctured disk. Exactly, that's right. Okay, and that will be done by one operation which is of course very familiar. I will write what it is. So, let us call this 1, 3, 2. 1 prime, 3 prime, 2 prime, okay, just to label the punctures. Okay. So, what we do is that we introduce two upper half planes. With coordinates z, z prime. Okay. One for this one, z prime for this one. Okay. Then we glue the two by identifying by the relation W2 W2 prime equal to minus q. So, the claim is that the result of inserting connecting these two by a propagator and summing over all states generates a new disk now with four punctures, okay, where they are identified by W2 W2 prime 2 prime equal to minus q. Okay. So, w, so z's are functions of w's, right. So, w's can be inverted to be written as functions of z. I will write this, I will write it here. So, exercise that z equal to f I of w I can be solved So, this is one place where the SL2R nature of the transformation is very useful because it can be easily inverted. Okay. So, W1 is alpha times 2z over 2 minus z plus gamma z. W2 is equal to 2 alpha times z minus 1 over z plus 1 plus gamma times z minus 1, and W3 equal to 2 alpha times 1 over 1 plus gamma minus 2z. This is just by inverting the these relations. Alpha and gamma were the two parameters in the conformal maps, F1 and F2 and F3. If you remember, let me, one was alpha, one was gamma, exactly, right? You are just inverting those relations. Okay. Q is real parameter, yeah, here. Yes. Exactly, that is right. Which, because it is a boundary, that is why K is real, right? We are just gluing the two boundaries by this map. Right? And the claim is that that is what comes in string field theory when you join them by propagators.
But when you cut this neck,
Yes.
then closed strings.
No, open strings.
But I'm saying that.
See, because this is a boundary, right?
Boundary, that's true.
So, it is only open string propagating in this channel. See, for this disk, there is no closed string propagation. Closed strings will be cylinders, right? Will be circles. Imagine that there is this disk, right? We are just pinching a neck, right? It is only a thin sheet that is there, right? Not a cylinder. Yeah, so this is exactly plumbing fixture.
They are usually set 1, Q to be 1, or any fixed number. Here Q is some running variable.
Yeah, because the Q is the Q of the propagator, right? So, this thing emerges not when you write it as a propagator as 1 over m square, but when you write the propagator as integral dq q to the m square minus 1. Right? For that part, every q there is a Riemann surface, right? And that is what you get here.
So when Q is a variable, that means you are going off shell and you are integrating over all possible momenta.
Well, even if q is 0, right? You can still be off shell, right? Because still all things are propagating. For example, tachyon is highly off shell, but that is the dominant contribution in the q goes to 0 limit.
Intuition behind this, I mean, as the throat becomes very long,
That corresponds to q goes to 0.
goes to 0.
Exactly.
Why is it this inverse map?
Okay, the inverse map, yeah. I mean, basically what happens is, it's something like this, phi r, if r is 1 and phi r prime the other one, right? Q to the power L0 phi s, something like this. Okay, q to the L0 minus 1, dq over q. Okay. So, what it is doing, this is like scaling by q. because there is an L0 sitting here, right, because the propagator is 1 over L0, okay, that we will see later. So, q to the L0 is like scaling, okay. So, it first scales say W2 prime to W2 prime over q, okay, and then because of this inner product, right, you have to take a BPZ conjugation, okay, that Z goes to minus 1 over Z, right, that is why this inversion, that is why you have this kind of inverse map. No, no, you will cover only certain region around y equal to 1. Okay. Similarly, for another diagram, you will cover another region around y equal to 0. Whatever is left, you declare that as a part of the 4-point function, the contact, this term, this contact interaction. Okay. But here there is no divergence anyway, so you don't have to, you can just do the y integral, right? Exactly, that is right. Okay. So, the boundaries, exactly, right. So, we want to find this map between y and q only locally near the vortices, because that is where the divergences are, right, and that is where we want to make this replacement. Well, which one? Well, yes, I mean not exactly, right, but they also require use gluing, but different kind of gluing.
Resulting moduli space is going to be the moduli space of this contact diagram, this 4-point moduli space plus the one that you obtained.
No, the Feynman diagrams, because these are coming from the Feynman diagrams, right, because that is, we are finding the moduli space associated with that one, part of the moduli space, right. That will cover the region near y equal to 0 or y equal to 1, because that is where the singularities are.
That's what the boundary of the moduli.
Exactly, right.
And the bulk is
Exactly, the bulk everywhere else where there is no divergences, right, that will come from here, exactly.
What exactly is the region near y equals 0 that is being covered?
We will see how what region, because once you know the map between y and q, right, you just have to see like 0 less than q less than 1 what it maps to in y plane, right.
So, two open string vertices can in principle fuse onto a closed string vertex or not? I mean, how come the intermediate propagators are all
Because here in this case, I mean what you are thinking of is a higher order diagram. Okay. On the disk, it does not happen, it is a disk amplitude, right, and on a disk amplitude the collision of two open strings only produces open strings. Yes.
So q equal to 1 in this coordinate, and so when you are doing this for a, you had these two different diagrams, right? So
Yes.
q equal to 0 from another coordinate. Is there going to be some interaction between these?
No, no, they will be completely separated. So the point is that the way you adjust, so for that is why I have taken a large alpha. We will see that if alpha is large, right, what will happen is that the q in the range 0 to 1, okay, for this diagram will cover only a small region near 1, right, and for the other diagram it will cover a small region near 0, right. Left over region is all coming from here. So there will be no overlap.
But if symmetrization is automatic in these coordinates,
Symmetrization we do not have to do it. Yeah, so that is why symmetrization is automatic, but still because of y equal to 1 and that is why y equal to 0 you can actually get from y equal to 1, yeah, right. You do not have to do a new calculation, but it is something has to be added by hand.
so we can just sew these two disks together only at W2 or
Exactly. So the same diagram, right, we just have to do a different kind of identification to get the region near y equal to 0 and y equal to 1, right, and just interpret this as different diagrams, but actual evaluation is the same.
so if you instead of doing this on a disk,
Yes.
this was being done say on a sphere out of a
Yes.
Is this, would this be, I mean, there would be, is there a version of this where you look at closed strings on sphere?
Yes. Q will be complex in that case, right. Yeah, for this particular problem you could, right, but often what happens is that the open string vertex opera on the boundary, right, and the boundaries sometimes admit the kind of vertex opera that does not have an extension to the bulk, right. So these are, you have to really treat them separately. Okay, so the idea is that we just have to use this, right, to relate z and z prime. Okay, Once you relate z and z prime, you have just z plane and you know where the punctures are, right. Z equal to, see, one puncture at 1 you have already glued. So, z equal to 0 and infinity, right, and then z prime equal to 0 and infinity, but you translate them into what it is, what they are in the z plane. So, let me just write the equation and then
You know Z in terms of W, I mean, from that map you will identify W2 and W2.
yes, exactly. So, let me write that equation. So, 2 alpha times z minus 1 over z plus 1 plus gamma into z minus 1 times 2 alpha z prime minus 1 over z prime plus 1 plus gamma into z prime minus 1 equal to minus q, right. So, that is all we did. So, now the idea is that z and z prime have been related, right. So, now the punctures, because you are gluing at 1, exactly, punctures at z equal to 0 infinity and z prime equal to 0 infinity, okay. But using this map we can figure out what it is in the z plane. So, this corresponds to z equal to 4 alpha square plus gamma square minus 1 times q over 4 alpha square plus 1 plus gamma whole square times q and 4 alpha square plus 1 minus gamma square times q over 4 alpha square plus gamma square minus 1 times q. Okay. So, these are the now 4 points located on the disk, right. So, all you have to do is to put one of them to 1, right, by again SL2R map, just scaling. In this case, it is just scaling, you can put one of them to 1, right, and you will put, so either one or this one or that one you want to put equal to 1, but you want to put the 1 such that the other one is less than 1, because you want y in the range 0 to 1, right. So, that you can do. So, we will define z hat by scaling, which is z times 4 alpha square plus gamma square minus 1 times q over 4 alpha square plus 1 plus gamma square on q, sorry, 1 minus gamma. Okay. Yeah. So, I put the second one to 1, right. So, this one will be scaled, right. So, the punctures are located in the z hat plane, the punctures are at 0, 1, sorry 0 y, 1 infinity. So, y after you do the scaling, it is 4 alpha square plus gamma square minus 1 times q whole square over 4 alpha square plus 1 minus gamma whole square q Is this okay? Right. So, this is the YQ map. Okay. And now we are going to use the fact that alpha we have taken to be large to just expand it out, because it is just easier to see what is going on. Okay. As I said, final results should be independent of alpha and gamma, but let us just expand this out. So, this for large alpha is 1 minus q by alpha square plus 1 plus gamma square q square over 2 alpha to the 4 plus order q cube over alpha to the 6. Okay. So, you see that indeed y is close to 1, but less than 1, right. Okay. And we can also see the range.
And you're using here the q is a positive number.
Yeah, I am using the fact that q is a positive number, exactly.
It's going to lie you're going to integrate between 0 and 1.
0 and 1.
And you just to be sure you get integrate between 0 and 1 because that's what will produce the propagator.
Yes, exactly, right. So, you are instructed to integrate q from 0 to 1, right. But okay, we will see exactly what we get. So, this range 0 less than equal to q less than or equal to 1, right. This corresponds to y between right. So, the idea is that between y this and 1 we replace y by q and do the q integral with the rules that I have specified. Right. In the rest below this we continue to do the y integral. Okay. Furthermore, this is necessary only for the term that is singular as y goes to y goes to 1, right. For the others it does not matter if you change variable or not change variable, right, it is the same. So, let us take this integral 0 to 1 dy 1 minus y to the minus 2, right. This is the term, the dangerous term near y equal to 1, right. So, this is what you have to treat carefully. So, this I am going to write as integral 0 to 1 minus 1 over alpha square plus 1 plus gamma square over 2 alpha to the 4 plus order alpha to the minus 6.
You don't need to keep the first Taylor expansion around y equals 1 the other half of the integral.
For the other part,
You've kept the most singular term.
yeah. So, for the other ones, right, we in principle you have to change the variable for the other terms also. But because of the non-singular, right, whether you change variables from y to q and you do the integral or whether you do the integral in terms of y makes no difference, right.
But I was thinking if you take whatever multiplies with 1 minus y.
No, nothing, it is a 1 minus y to the minus 2.
Minus 2, there was something. Oh,
No.
the whole thing was that.
Yeah, the integrand had a 1 minus y to the minus 2 plus y to the minus 2 plus 1, yeah, nothing else. Okay.
Yeah.
So, this is part of the integral, right, and the idea is that the rest in this range we are going to convert from y to q. So, we also use one more thing from here that we can check that 1 minus y to the minus 2 dy is minus no, alpha square q to the minus 2 dq plus order alpha to the minus 2. Okay, this is again by changing, knowing the relation between y and q, you can see that this is true. So, in the next part, yes, exactly. So, that is why I have written it as y, right. The other range I want to change from y to q, right. For that I need to use this relation because I want to write the integral in terms of q variable. Okay. So, in the other range the integral is alpha square integral 0 to 1 dq q to the minus 2. Okay. There is no q inverse term here. Okay. If there is a q inverse term, we have to just remove it by hand, just subtract it off. This is divergent, but we are supposed to replace it by minus 1, right, because that integral dq q to the beta minus 1 is supposed to be 1 over beta, both for positive and negative beta. So, for beta equal to minus 1, right, this is minus 1. Okay. So, this is minus alpha square, this integral is elementary, you can easily do it, right, dy 1 minus y to the minus 2, no singularity. Okay. So, after you do that and add up everything, you find that this is gamma square minus 1 by 2. No, I have taken large alpha. I have taken large alpha, right? If there is, if you could do this also not for non-zero, not large alpha, right? I have just only kept the term that is alpha independent, that survives in the alpha goes to the infinity limit. That's just convenience, right? You could have kept the alpha dependent term.
So the second term has a large alpha square thing multiplying it. Oh, I see.
That gets cancelled against this one.
I see that. Yes.
Okay, so finally there is no alpha square. Okay, so let me just say that the other one can be dealt with in the same way. Yes, because the transformation is basically starts with linear. Okay, it's not always true, right? It depends on how you have chosen your variable y, right? Sometimes it may start, if there are more than one q, then y may start with q1, q2, for example, right? So it's not always that it's linear. Yeah, it's not a canonical variable, right? It depends on how you have parameterized your moduli space. Yeah, not by 1 but minus 1. Yes. No, no extra normalization. See, there is a overall normalization ambiguity in the amplitude, but that I have set equal to 1 anyway, right? That just comes as overall factor. Otherwise, there is no further ambiguity, right? All I have done is I have changed variable from y to q, right? And then I am using the rule that this integral is supposed to be minus 1, right? By this, because that's what we see from the string field theory interpretation of this divergence.
So, this alpha parameter,
Yes. Yes.
then that thing is a well-defined integral.
This one, yes. That's what I did. I just did the integral explicitly for this. See, the interpretation of this is that this is coming from the 4-point contact term. There is no divergence there, right? This is the one that is associated with the propagator, right? Which I use the propagator interpretation to get the result.
And by making alpha large, you make almost all of the integral contact terms.
Exactly, that's right. Because
Part of it is
exactly, that's the idea, right? That by making alpha large, only a minute part will come from the propagator, everything else just comes from the contact term. Right? But that's just convenience, you could have changed alpha, right? Because final result is supposed to be independent of alpha and gamma. Okay. So similarly, we can evaluate the other one, 0 to 1 dy y to the minus 2. Okay. As I said, it doesn't really require new analysis, right? So what one has to do is the following. You see, we have 0, y, 1, infinity, right? This is the way we had arranged this. Now we want to make, so these two are closed, right? Now we want to make 0, y, right? 0, sorry, thank you. Okay. So we want to make it into 0 and y closed, right? But y should be larger than 0. Okay. So basically you have to look for an SL2R map where this goes to 0, because the one, this is next, this is on the right of 0, right? This should be, y is on, should be on the right of 0. So this should be 0, this should go to y, okay, whatever you define that this goes to y. Infinity then should go to 1, because that comes next, and this 0 goes to infinity. Okay. So basically you look for an SL2R map, okay, call this y prime. You look for an SL2R map where, which takes 0 to infinity, y to 0 and infinity to 1. Okay. Then whatever happens to 1 is our new y. Okay, that gives a relationship between y and q again, but this time for 0, as q goes to 0, y is goes to going close to 0. Okay, so using that you can again find a change of variable between y and q near the point 0, when y is near 0. Okay. But I will just write the answer, this is also given by gamma square minus 1 by 2. And finally, you have the 0 to 1 dy, that is the third term, it is just 1, okay, there is no divergence over here. Which takes you from this, see you can, okay, you can try to work this out. If you want me to do this, 0 should go to infinity, so that should be a z in the denominator. Okay. Then y should go to 0, so that should be a z minus y, okay. And then infinity should go to 1, yeah, so this is the SL2R map, right. This takes you from 0 to 0 goes to infinity, right. Y goes to 0, right, and then infinity goes to 1, right. So whatever happens to 1, right. So the new y prime then is 1 minus y by 1, right. That is 1 minus y. It is easy to see. So basically the near 0, right. If you want to find the change, the relationship between y and q, right, you just replace y by 1 minus y in this formula.
SL2R is a convenience rather than, I mean, you could use some other maps.
Well, here no, this here you need SL2R, because if you use some other map, that it will become a non-upper half plane, right? Because you want to write it as an upper half plane correlation function. But the fact that FIs have been chosen to be SL2R is a convenience, right? See, if they are not SL2R, right, then after you glue, right, you have to find a new coordinate system in which it looks like a upper half plane, right? There is a uniformization theorem which tells us there always exists a new coordinate system by which you can make it into upper half plane, but that requires solving differential equations. Here you just did it purely algebraically, right? That is the advantage of using SL2R maps.
And sir, even without doing the calculation, it was clear you could get the same answer for those two divergent terms.
More or less, because they are symmetric, right? Okay. Yes.
Why? I understand that we are getting this divergence 1 minus y quantity square.
Yes.
Our y square, second order, from the vertex operators. But why are we integrating it from 0 to 1? Why are we looking at that?
Because the amplitude has this, the full integral, right? So the amplitude, let me write. So the amplitude expression that we had was integral 0 to 1 dy 1 minus y to the minus 2 plus y to the minus 2 plus 1, right. So we are just dealing with this term for now, right. This is the one which has singularity near y equal to 1, right. Yeah, because so see, in principle you should do change of variables for all of these, right, but for these it's irrelevant, right, what to do near y equal to 1. So you could just integrate from y equal to 1, right. So for this one we have to keep treat carefully near y equal to 1, and this one similarly we treat carefully near y equal to 0. Okay, but now let us add them up, right. So gamma square minus 1 by 2, gamma square minus 1 by 2 and 1, right. So the sum is gamma square. So the sum is gamma square. Okay. So this basically contradicts everything that I have said so far, right? Because I said everything should be independent of alpha and gamma, right? It's not independent of alpha and gamma. I say it should be 0, right? It's certainly not 0, right? So basically you have missed something, right? But to understand what we have missed, okay, we have to do a little more string field theory than what we have done so far. Right. So next time we will see using the full-fledged string field theory. Fortunately, we only need to do a kinetic term, right? You don't need the interactions. Okay, we can see the difficulty just by examining the kinetic part of the string field theory. So that's what we will try to do next time, right? What we have missed in this analysis.
So here we have not really done use string field theory at all, because we are just doing that first correlator with certain chosen technology.
See, the string field theory is the way where I have done string field theory is this fact that the y to q map is given by this gluing relation, right? Because if I change my FIs, right, string field theory vortex, then the result will change, right? As you can see already that it depends on gamma, right? I mean individual ones in fact depend on alpha, gamma, everything, right? Because I have just taken the alpha large limit. So string field theory has gone in, right, and the result depends on what particular string field theory you have used, right? But if it is really true that the defined formulations are related by field definition, then nothing should depend on what string field theory you have used. Okay, so I think I will stop here.
Sir Gopal, questions?
Oh, they cannot ask. They can call you.
Oh.
You call.
If you have questions, maybe you could call Gautam.
Gautam is calling you.
Now,
No, she's calling. Oh, she's because she can tell us. No, when you call.
Yeah, she is dialing.
Typing in this, maybe to say that.
Yeah, I think maybe just call her. It's easier.
Just hold your phone up. Please go ahead. Okay, I'll just.
Okay, she says please go ahead.
Yeah, please go ahead. That's what she said.
I think it means no questions.
Yeah.
No, Gopal, you have no questions. Is this correct? If you have questions, put your hands up.
There are questions.
Yeah, question. Yeah, just call.
Email question.
Okay. Okay.
Okay, fine. So we don't have to do that.
Okay.
Okay, connection just came on. Hi, Navamita. So,
I
yeah.
said I'll just email my questions because like probably it would be difficult.
Okay.
Okay. Okay, all right. Yeah. Okay.
You can go ahead.
Okay.
Thank you. Bye.
how about here? Any questions?
Yes.
So these conformal maps you have chosen, these F1, F2, F3, are these like arbitrary, or you could have chosen some other conformal map?
Yeah, I could have chosen other conformal maps. The point is I chose SL2R maps because it's just easier to deal with, right?
There is this symmetrization in this coordinate.
Yeah, so there is a symmetrization involved, right? If you choose arbitrary conformal maps, you have to explicitly symmetrize, right? But because I chose them to be cyclically symmetric, right? That's why I didn't have to do the explicit symmetrization. But that's again a matter of choice, right? You could have chosen other conformal maps. So the idea is that if you can choose anything that you like at the level of the 3-point function, there is no constraint at all. Okay? At the level of the 4-point function, there will be some constraints, but at the level of the 3-point function, there is no constraint. You can choose anything that you like, right? But at the end, the final result should be independent of that choice. If it's not, then that means you have done something wrong, because in string field theory, there is a general proof that the results are independent of the choice because they are just related by field definition.
So, if I can ask you, the general proof is that you choose roughly the analog of any metric around each vertex, and then it doesn't matter.
Yes, exactly. Right, but we see here it does seem to matter, right? So that means there is more to it than what you have seen so far. Yeah, but that's what it amounts to.
Suppose we were interested in the diagram with two closed strings, but closed
Yes.
string vertices also on the disk.
On the disk, yes.
Then you would choose once again 3 of the operators as open, the open operators to be fixed, and 1 integrated. Suppose we were interested in 4 open string insertions
Yes.
and 2 closed strings.
Okay.
So
Then there will be altogether 5 integrals to do.
right.
Yes.
We could choose those 5 integrals as the 2 positions of the closed string.
Yes.
and
No,
one
4
guy-
positions of the closed
4
string.
positions of the closed strings and 1 guy on the.
Exactly.
And now, does anything funny happen when the closed string approaches the open string vertices? Does,
Yes, because as long as what propagates in the intermediate channel is open string, all these issues will arise. Because the point is, typically when the closed string propagates in the intermediate channel, see there are various degenerations, right? So whenever there is a degeneration in which the closed string propagates in the intermediate channel,
Yes.
that is okay, because that you can regulate using momenta,
yes.
right? When there is a degeneration, there are open string propagates in the intermediate channel. That's a strip degeneration,
Yes.
right? There, all these problems will appear.
So are there new divergences because when the closed strings approach that you need to regulate in this manner, that when a closed string approaches one of the open strings?
No, same, because it will come from the intermediate open strings, right? That's what you are dealing with, right? So far we have dealt with intermediate tachyonic open string, right? And the zero modes that come from collective coordinates, right? What we will see is that the part that we have not dealt with, that there are additional zero modes which are not collective coordinates, okay, which are in fact not showing up directly in this analysis, because otherwise you would have gotten a 1 over q. You see the dq, the q inverse term vanished completely, right?
Yes.
Because you just got a q to the minus 2 term, and then there is a finite term, right? So in this amplitude, you don't see any intermediate zero mode propagating. Nevertheless, there is a problem, right? In anticipation that there will be problem at higher order, right? We will see that we have to change what we do at this order.
I see. So, but if you put the closed strings, you would see this 1 over q inverse? I mean,
Yes, you could, yeah, depending on how you, exactly. So here the reason that you are not seeing the 1 over q inverse is because at least del x mode is not propagating, because 3-point function of 3 del x is 0, right? By the x goes to minus x symmetry.
Three photon problem.
Exactly, right? And the other zero mode which is responsible for this additional problem, right, that also does not propagate in this particular case. Okay. So I think that what you are thinking, maybe one can a simpler example, right, version of where these kinds of things will appear is when you have closed 2-point function of closed strings on the disk, say, right? Okay. So in this case also there is a degeneration, okay, when one of the closed string approaches a boundary, right? So that corresponds to a degeneration where it's like this. Okay, again a strip degeneration. So that will have exactly the same kind of problem.
Right. I see. So all of these, apart from the fact that you also get a q inverse, though there will be more complicated amplitude, this part will be more or less universal.
Yes, exactly, right? So mainly once you understand how to deal with the tachyon and the zero modes, we are done for the whole thing, right? You don't have to do, I mean, it's not every diagram requires a new physics, right? We just have to understand how to deal with the tachyon and the zero modes, because those are the sources of divergences.
The tachyon, as you say, is the closed string.
No, open string tachyon. The q to the minus 2, right, that we are seeing, that is coming because there is a state C, right? Open string vertex of C, that has dimension minus 1. Right? That's what is responsible for the q to the minus 2 divergence.
Yeah, this was q to the power L dot minus 1.
Yeah.
So when L dot was minus 1.
Yeah, and the point is these kind of divergences are also going to be there in superstrings. It's not specific to bosonic strings, right? If you have supersymmetric instantons, then the tachyons are not there, but the zero modes are very much there, right? The zero modes which correspond to translation, and also the zero modes that I will be discussing next time, which are coming from the ghost sector, those are present also in superstrings, right? So this has to be done also for superstrings.
When we have this disk with closed strings,
Yes.
then we would like to take this first, take the closed string to the boundary, and then get our open string operators, and in that description you would have a regulated divergence, and also to when you bring the open strings close together.
Yes, exactly. So the point is that there are various degenerations, right? One where correspond to closed strings coming together, those are closed string degenerations, right? There you don't have to worry. But any degeneration that has open string propagating in the intermediate channel, that's where you have to worry.
Here you don't have logs, but you might have logs in this example when you have some zero.
Yes, indeed, because here the point is once you insert some momentum here, right, then the C del x can propagate in this channel.
And then your point is that in this formalism you have a nice measure. In
Yes.
string field theory you have a very nice measure, and that will explain last book.
Exactly.
You have to do all this to get a finite answer.
Yeah. Right. So if you have C del x, then you will get some dq q inverse. This you remove, okay, but then you compute things with external del x's, and then just integrate over phi, right? You just integrate over phi without any additional measure, right? Now it may happen that in order to change from phi to xi, the xi is the collective mode, right? you may have to make a field definition, right. If that induces a measure, you include it explicitly, right. But in terms of the string field, there is no I mean ambiguity as to what the measure is. Yeah, that's just D phi.
Sorry, a vague question. So after doing all this, can you formulate an effective rule for string perturbation theory so that you would get the right answer?
This is the effective rule.
I know.
You are asking whether you can formulate a rule which doesn't require the choice of the FIs.
Yes, I suppose.
Right?
Yes.
That's what, yeah, I don't know. I hope that there is such a rule, but I don't know how to do this with the current understanding, right. I mean, we know for sure that if we choose the FIs, do the correct thing, final result shouldn't depend on the FIs, right. But the question is whether you can avoid introducing these FIs altogether, right. That's what, yeah, I don't know right now.
You know, for example, that in the 1 over 1 minus y, so the y going to 1 kind of singularity.
Yes.
If you look at the upper limit, it appears like you are drawing a radius. I mean, you're drawing some kind of a cutoff around 1.
Yes.
Of a size which is 1 over alpha square.
Yes.
And presumably in dealing with the other segment of the integral, you will do the same thing around 0.
Yes, but the point is, you see, 1 over alpha square is not enough. You have to keep the next term, because 1 over alpha square, when you do this integral, right, you will get an alpha square, because 1 over 1 minus y to the minus 2, right. So you need the next term also, okay, because otherwise you will get a wrong answer.
Okay, that kind of a cutoff prescription is, of course, going, there's gamma there. And all
Yeah,
that
so it's not just arbitrary cutoff, right. So whereas at the end we know that it should be independent of gamma and alpha, right, if you do everything correctly. But how to do this without going through the introducing these f's altogether, right. The point is, one would expect that maybe there is a procedure, right, but at least
So at some point you were saying something. At some point you were telling me about a cohomological way of doing things with the descent relations. It's very vague, but which seems like an alternative to that.
it's not really an alternative to that. This cohomological way of doing things is basically to a procedure for constructing the higher order vortices for a given 3-point vortex, right. So 3-point vortex from this perspective is completely arbitrary, right. But then given this, the 4-point interaction vortex, right. So first of all, you know that the 4-point interaction vortex should be such that it fills the missing region, right. This has that certain radius around alpha equal to 1, then the other diagram has certain radius around alpha equal to 0. It should fill the intermediate range, right. But now we have to introduce the local coordinates around the 4 punctures, right. And the only constraint that we have is that the local coordinates must match up whatever is induced from the 3-point vortex at the boundaries, right. When y reaches the boundary from Feynman diagram, you have some local coordinates that should match up the 4-point function local coordinate. But in the interior, again, it's completely arbitrary, right. So this cohomological way of doing it is basically this descent relation, right, which relates 3 to 4-point function, 4 to 5-point function, and so on. There is something in BV which is called minimal model, right. I don't understand it very well, but apparently what that does, I mean, it's an abstract I mean formulation in BV, but apparently what it does is to directly give the S matrix. Okay. So it's like an extreme version which doesn't go through the off-shell formalism, right. But it's not completely clear that that can deal with problems of this kind, right, the divergences of this kind, because S matrix, the naive S matrix doesn't make sense, right. You have to actually remove these things and then do the integral.
So suppose we were working with a higher brain,
Yes.
so that analytic continuation will be one approach.
Yes.
So we choose not to analytically continue.
Yes.
We can still work it out this way. Now, this like in the case where you have some closed string vertex operators and you put these, and I suppose one way we're interested in not putting any vertex in. Yeah, we're interested in some amplitude with no vertex operators on the disk.
Yes. Yeah.
could have put that. But there we will, and think of this as putting tachyon at non-zero momentum and then analytically continuing to, no, but that's not the same. Sorry.
In higher branes, yes. I mean, in higher branes, as long as the open strings carry momentum,
Yes.
right?
Yes. Yes.
Okay.
Yes.
The point, first of all, as if the open strings carry momentum, then they are interested in them also as external states because they are physical objects. Right? It's not transient objects anymore.
But since I want the analog of this object,
Yeah.
I will be interested in no vertex operators on the boundary.
Fine. Okay.
But I can define it anyway by putting tachyon vertex operators in the boundary and taking momentum to zero.
Yes.
Right. But I was just wondering, is that correct? I mean, that would be like n boundary tachyons
Yes.
with two closed strings. At zero momentum, is that the same as having just? I'm sorry, I'm asking very stupid questions. From the worldsheet point of view, putting just identity at these points seems like you're doing nothing.
Yes.
But from space-time point of view, that seems like it's giving you a different process.
Yes.
How are these two things consistent with each other? How come?
Yeah. Because the identity, right,
Because the C
is
goes-
not nothing. Yeah.
Yeah, because the C goes.
Exactly. Because there is a C insertion there.
Thank you.
Yeah.
So if we were to have this integral over modular space with some choice of coordinates of the modular space, is there a way to somehow just locally identify the right coordinate in the degeneration? The right
The Q.
coordinate,
You mean the Q? Yeah. See, the point is there is no right Q, right? Because as you saw, it depends on alpha and gamma. So it's not that there is a unique correspondence between Q and Y.
But let's say if I assume that it's going to be independent of all that.
Yeah, whether there's a canonical way to associate Q. Yeah, I don't know. I mean, that's what one would like to have, that where you make it manifest from the beginning, or you don't have to even have to make it manifest, that you assume that it's independent, you already know, right? Can you find a canonical procedure which avoids going through all this? Right? I mean, here, for example, you could probably choose F in such a way that Y is directly equal to Q. So, here Y equal to 0, Y is equal to Q. Okay. That means that near Y equal to 1, the relation is complicated. Because if you just assume that Y is Q, near Q equal Y equal to 0, and Y is 1 minus Y is Q near Y equal to 1, you are suddenly going to get the wrong answer. Right? Because then both of these will just become minus 1. Right? This will be like minus 1, this will be like minus 1, because you are doing 0 to 1 Q to the minus 2, and this is plus 1. Right? You will get it as a minus 1.
So just one more.
Yes.
Again, it's not making sense, but anyway, let me say. Suppose I put m tachyon vertex operators on the boundary in a higher in where the number of Neumann directions is p,
Yes.
and however many
So you want to put on shell tachyon or off shell tachyon?
on shell tachyons, but I'll eventually take p goes to 0.
But that will not be on shell.
So it's not on shell.
You have to put P. Yeah.
I was hoping you could do a dimensional continuation.
See, the best option is to try to put, as you said, that assume that there are these additional directions, right, and there are momentum in the additional directions, right. So, if there are momentum in the additional directions, as I said, that it's not that it will reduce to the original answer, the answer that you want, because there are gauge fields in the del x prime is propagating, right.
Yes.
So, you could try to remove them explicitly, right. That's one possible way to do this.
So the dependence on gamma, this gamma, the final result.
Yes.
I mean, it's not so surprising perhaps because you are doing an off-shell calculation, and so of course, the result should depend on the choice of the little metric in the patches that you are doing. So why shouldn't it depend?
Yeah.
on
So, if you look at the calculation, yes, indeed, you say why shouldn't it depend on gamma? But as I said, the string field theory guarantees that it shouldn't depend on gamma, because different choices are related by field definition. And the actual calculation that you are trying to do is on shell calculation, right?
External vertex operators
Yeah.
are all on shell.
That's true, but I'm saying that in the middle,
Yeah.
you
We have gone off shell.
in which certainly all the Beltramis should come back in and so on because
Yeah. should go away. Yeah, from the perspective of this calculation, it looks like a magic. If somebody had just given you this calculation, right, then it will be very surprising why the alpha gamma dependence should go away, right. But on the other hand, string field theory, right, there is a formal proof in string field theory that these changes in alpha and gamma can be removed by Fourier definition. Okay. See, otherwise this whole thing will not make sense, right? Because you don't want something that depends on alpha and gamma. Yeah, so the formal proof is the following, that you start with a given string field theory, right, in the BV formulation, and then you ask what happens if you deform these FIs a little bit, okay, subject to the internal constraints that have to satisfy, right. The 3-point function can be deformed arbitrarily, but then 4-point function has to be deformed appropriately so as to satisfy the constraints. So, given a arbitrary deformation satisfying the constraints, you show that in the BV formalism, right, it can be undone by what is called a symplectic transformation, okay. And symplectic transformation is a symmetry of the BV formalism, right, that is just a Fourier definition, and then all physical quantities you can show are independent of such a symplectic transformation from the perspective of BV formalism. Yeah, so that's the formal proof, but it's not that it goes vortex by vortex, right. It requires that all the vortices have some internal consistency condition.
There can be mixing between different words.
Exactly, because if once you choose a 3-point function, right, the 4-point function, there is still a lot of ambiguity, but it's not completely arbitrary. You cannot just choose F1, F2, F3, F4 arbitrarily and integrate over an arbitrary part of the moduli space, right, because we know that it has to cover up ultimately the full moduli space, right. In this case, this missing region has to be covered by the 4-point function, right, and then you also want that the off-shell amplitude should match at the boundaries where the Feynman diagram and the contact are meet. Okay. So, those are the consistency conditions that the FIs have to satisfy, okay. And then you can show that given those consistency conditions, any deformation of FI that is consistent with those automatically induces a symplectic transformation.